Okay guys, in this video we're going to talk about how we can use what we've explored with linear equations so far in order to help us, describe the relationship between two variables, say height and weight. And so what we're going to be doing is writing the equations of lines really, but using that equation of a line to describe what's happening with a set of data. So that's why this falls into our linear section, or section 1.3. So we're going to start by taking a look and a few basic vocabulary and concept ideas here. And the first one is we're going to start with what we call a scatter plot. Now, vocabulary-wise, we say that a scatter plot has points that show the relationship between two sets of data. And so really what this is just a collection of points x and y that when we graph them describe the relationship between two sets of data. So in this relationship here, you can see that there's a weight and a height relationship. And as weight is getting bigger and bigger, we can see on average our height values are getting taller and taller. And so we can kind of describe a relationship here just by looking at how these dots are arranged with one another. So when we describe the relationship the dots between two variables in a scatter plot, we tend to use this word correlation. And so what I want to do is kind of break this down really quickly here. Correlation or correlation is made up of co, meaning together, and relation, meaning how things are related. So when we look at correlation between two data sets here, we're really looking at how strongly linked they are, or maybe how weakly linked they are. So correlation is defined when the two sets of data are strongly linked together. We say that they have a high correlation. We define it as the connection between two data sets here. So with respect to types of correlation, we want to make sure that we touch on a couple of positive and negative. And so just to be clear, when we talk about a positive correlation, we say a correlation is positive when the values increase together. And what we mean is this: as x increases, y also increases. So the definition of a positive correlation would be where when one is doing one thing, the other one's doing the exact same thing. So when you look at the examples down here that I've got a screenshot of, we can say that a perfect positive correlation would look something like this, and it would occur in a straight line. When you see a high positive correlation, these are these instances where as x is getting bigger and bigger, we can see that our y variable or our y values are getting bigger and bigger as well, just not perfectly. So we would refer to this as a high positive correlation, whereas this here we can still see as one's getting bigger and bigger, the other one's getting bigger and bigger, but not as closely connected. So we would call that a low positive correlation. No correlation would be this maybe scatter plot where the x and the y don't seem to have any relationship with each other whatsoever. Now, the other type of correlation we refer to is negative correlation. We define negative correlation as when one value decreases, the other increases. And so we can put it this way: as x increases, y decreases. And this is like I suppose you can use the converse as well. As x decreases, y increases. So when you look at these negative correlations here, a perfect negative correlation would be as x goes up by a certain amount every time, y is always going down by the certain amount. And so we could describe that using a negative slope here. But negative correlation, you can see a high negative correlation and a low negative correlation. In any of these instances, as x is going to the right, as that's getting bigger and bigger, our y values are decreasing. Or as our y values are growing in height, we're moving back from the right to the left, so our x values are decreasing. So when we talk about the connection between our variables, we'll use the word correlation, and we'll describe our correlation using either a positive, negative, or no correlation to describe the relationship between data. So what I want to look at is an example of a data set that I have here, or I've grabbed. It says the local ice cream shop keeps track of how much ice cream they sell versus the noon temperature on that day. Here are their figures for the last 12 days. And so this is kind of a neat thing. You'll notice that when you look at the table here, it says temperature in Celsius and ice cream sales on the right here, and that would be in dollars. First thing I want you to know is that I could switch these two columns around, and it really wouldn't matter very much in terms of the connection between these two variables. The only thing that would impact is what we're going to decide to put on our x-axis and what we're going to decide to put on our y-axis. So because we want to keep track of ice cream sales, maybe it makes more sense to put ice cream sales on our y-axis here and then temperature down on the bottom. But again, like I said, we can switch these two axes around and it won't impact the amount that these connect, because these two functions, it seems if you look at how this data has been graphed over here, graphing all of these data points, it looks like we have at least a strong positive correlation. So when we talk about what is the relationship between temperature and ice cream sales, one thing that we may want to mention here is this, that there looks like a strong positive correlation between ice cream temperatures. We'll do temperatures first since it's our X variable here. Temperatures and ice cream sales. And so we would want to write this right here, but it seems that as the temperature goes up, they sell more ice cream. And so I would think that that'd be a reasonable conclusion to draw, but the data just really reinforces this here. And so what I want to do is I want to talk about a way to describe data points or the relationship between two data sets using a line. And we're going to refer to this line as a best fit line. Now, when we talk about a line of best fit, it is a line that is kind of describing the relationship or the pattern that's going on between our X and Y variables here. So you'll notice here that it says we can draw a line of best fit, but that it's also called a trend line on our scatter plot. And this trend line's job is just to basically describe the trend between the data. And so if I had to say, is this a good line of best fit? I would say that this is a good line of best fit, but the reason why is because there's just about as many dots below the line as there are above the line. And there's no rule that says there have to be as many on top of the line as there are on bottom, but that's a good indicator. And the other thing is this, it's as close as we possibly could get it to all possible points. Of course, you're not going to be able to get a line running through all of these points. That's not a line. But we're going to try our hardest to get this line to run through all these points. So we want to have it as close as possible to all points, and it should about split half as many above or as are below the line here. But this line of best fit, the reason why it's really helpful is because we can start to look at what would have been some data points here, say for like 21 degrees where we don't have a graph. We could trace it up to this line and say this line is about at this height at that input value. And so what this allows us to do is kind of try to make predictions about the data based on the data we've already seen. It's kind of a neat thing, play detective. So this type of prediction that you see me using here, say to find out what our sales would be around 21 degrees, because this prediction lies within our data set, we're going to give it a specific name here. And that name is interpolation. Inter, the prefix inter means between. So when we talk about interpolation, we're talking about trying to draw conclusions using this line that we've drawn here based on the middle of the data or data that occurred within the data set here. So interpolation is where we find a value inside our set of data points here. So for instance, 21 degrees, I could trace this up to my line of best fit and trace it over and say, you know, it would be about a good guess to say $480. Now, do we know this is going to happen? No. But based on the evidence suggested by this trend, we could say that it is likely to occur. So here we are using what we call linear interpolation to estimate the sales at 21 degrees Celsius. I would like to argue next that maybe we have a data point that didn't occur in this graph. And so, excuse me, I suppose what I would indicate is, what if we were to go out to like 27 degrees, 28 degrees, excuse me, we're going by twos down here. We do not have a data point for 28 degrees C, but we could go outside of the data set using this line of best fit and try to make an educated guess based on that data point and that line of best fit there. And so because this is outside of our data set here, we're going to refer to this as extrapolation. So as an example, extrapolation is where we find a value outside of our data points, our set of data points, using our line of best fit. And so as an example, at 29 degrees, if this trend is to continue beyond the data, then our 29 degrees would intersect our line here, and as we trace that over, we could estimate maybe around $740 worth of income here. So you'll notice it says here we use linear extrapolation to estimate the sales at 29C, which is higher than any value we have. So the thing we need to be careful of with extrapolation is this. It can give misleading results because we're in uncharted territory is what this says. Basically, who's to say this pattern is going to continue forever? I mean, let's face it, if we get up to 40 degrees C, you guys, that's super hot. Nobody's going to leave their houses, and they'll probably lose sales. So interpolation will be very strong. Extrapolation is kind of like making an assumption here. So what I want to do now is talk about, could we come up with an equation that relates our temperature values to our sales values, such that all I would have to do is plug in a temperature and it would produce a sales number. Or vice versa, if I knew a sales number we wanted to hit, we could work backwards to try to determine what the temperature at noon would have to be. And so in this slide here, we're going to look at how we would write the equation for a line of best fit. So you'll notice that I've broken this down into steps, but this is the same set of data that we had before, and this is the same scatter plot that we've already got here. And I'm going to use the line of best fit that was already provided on this screenshot. But the first thing we want to do is really just choose 2 points that are very close to your line of best fit. And you'll notice I say the further apart they are, the better. So with respect to our data over here, I notice this line gets really close to this data point right here. And I feel like maybe this one here, I mean, especially this one here, is really close to our line of best fit. So what I'm going to do is I'm going to indicate what these 2 points values are, and I may have to go back and look at my data table. So this right here, this looks like between 16 and 18 degrees here, closer to 16. And as I look at the data, 16.4 is the most reasonable data value here. So I'm going to write 16.4 is our X value, or our temperature value. And I'm also going to write 325 is our Y value, or the amount of sales. And up here on this point, this was our final data point, so the highest temperature. I think 25.1 to me looks like the highest temperature here. 25.1 degrees produced looks like $614 in sales. So the first thing we do is we just choose 2 points that are really close to this line, but then we're going to use these 2 points to help us write the equation of this line. So remember, when we want to write the equation of a line, we need 2 things. We need a slope and we need a point. And when we write the equation of a line, using a point x1, y1, and a slope m, what we're going to say is we use this point slope form, which was our y minus y1 equals m times x minus x1. So if what we need to do is write the equation of this line, I would start with the fact that we need to know the slope of this line, and we're going to use these 2 points here to kind of try to find our rise over our run. So number 2, our second step here, we're going to use our slope formula, y2 minus y1 over x2 minus x1, in order to deduce the slope of this line. So our y2 in this case is 614, so we have 614, minus our y1, which is 325. That's going to tell us how much our sales increased by. And then if we look at our x2 minus x1, we get 25.1 was the temperature at the second data point, minus 16.4, which is our temperature at the first data point. So we're going to need to get our calculator here, and we're going to do a little bit of approximating out to the nearest tenth. But if we did 614 minus 325, we get a value. And if we do 25.1 minus 16.4, we're also going to get another value here, 8.7. So we get 289 over 8.7. And what I want to do is I want to boil this down to just a decimal where we're going to round to the nearest tenth. So I'm going to say this is approximately 289 divided by 8.7. And so what we discover is the slope is about 33.2. So I'm going to write 33.2, but what I really want to make sure that I mention here is that this was dollars over degrees. And so when you look at this 33.2, it's like 33.2 over 1. It's like saying that our graph would go up $33.2 for every 1 degree. And so as we interpret our slope here, it's going to tell us the rate of change of our graph. Now that we have a slope, step 3 says use your slope and one of the points you use to find the slope to write the equation of the line using point slope form. So now we can use our point slope form, except for we have to choose one of those 2 points that we had used to find the slope in the first place. And so I'm going to go ahead and get ourselves set up here. But out of both of these points, 25.1 and 614, and 16.4, 325, I'm more inclined to use the smaller values. So I'm going to put in 325 as the y value for our y1, and our x1 is 16.4. From here we just need to work on distributing and then adding the 325 back to the right. So we get y minus 325 is equal to 33.2-ish x minus, and here's where we're going to have to use a calculator. Suppose we got to take 33.2-ish times 16.4. And we know that we're multiplying a positive times a negative, so this will be negative, but 544.48, we get minus 544.48. And so as we add 325 back to the right-hand side here, 325, I suppose we could say y equals 33.2x. And using our calculator here, this, if it were negative, I'll take this times a -1, make it negative. And we added 325 to this, so plus 325, what we would get is our y-intercept at -219.48, so minus 219.48. So put a box around this and celebrate, because this equation right here, as step 4 says, we can use this equation to either interpolate or extrapolate based on the data. So that is to say that maybe we go back to my initial question, which was I wanted to find the ice cream sales if the temperature is 21 degrees Celsius. So in this particular case, we're given a temperature which out of our data here is temperature x or y. Temperature is x. So what we're going to do is we're going to use our equation y equals 33.2x minus 219.48, and we're going to substitute in for our temperature value, or our x value, 21 degrees. And so what we would get is this new expression, which if we evaluate this on a calculator, we have 33.2 times, in parentheses, 21, and we're going to subtract off 219.48. It looks like we would get 477.72. So I'm going to write 477.72. But here's the thing, we were drawing a conclusion, and that was to say what is our y value, or our earnings amount, at 21 degrees Celsius. So you could go back and look at our interpolation picture here. It said about 480. Using our line of best fit, we were really, really close, about 477.72, and that was using a more accurate model. So now what I want to do is I also want to interpolate, but what I want to do is take a different approach. What if I want to find the temperature? So in other words, find x when I give you a y value. This time I'll give you the sales. So at 400 degrees, if I had to guesstimate, I'd say it'd be about right here, and it would go down and hit our temperature axis about right here, maybe a little below 19. But this time we're using the same equation, except plugging in for our y value and solving for x. So we are going to substitute in for our sales here, or our y value, $400 in sales, and this would equal 33.2x minus 219.48. And so our job here would just be to solve for x. So as we add 219.48 to both sides, so 219.48, we're adding this, we would get on the right hand side 33.2x, and on the left hand side we get 619.48. And so if these are equal, then the only thing we have left to do is divide by the 33.2, and if we take 619.48 and we divide by 33.2, we should get something that's pretty close to what we would identify visually up on the graph, but about 18.7 degrees. So I'm going to write approximately, and I'm going to write 18.7 degrees Celsius here. So you can see how scatter plots show us the relationship between data, but by using a line of best fit, we can either interpolate or extrapolate, and even write the equation of that line to give us a predict accurate values based on our model here. Cheers.